So I'm Tomas Aquino, for those of you who don't know me. I'm going to write it down just in case. The reason I pronounce it funny is I'm originally from Portugal. But these days I'm at IDEA CSIC. So this is part of the CSIC institution, which is like the Spanish CNRS. It's the Spanish National Research Council, I think is the official translation in English. And it's in Barcelona, right? Just for reference. So you may be, or not, depending on your preferences, scared to see this up. Yes, I'm going full board today. So that was a bit of a gamble, but I think, so I'm going to do some solutions for basic cases for the advection-diffusion equation. I think you should see that at least once if you haven't yet. And seeing it twice is not bad either if you have already. So hopefully it won't be too mathy for most of you. I'll try to keep it relatively simple. But again, I think it's important to get down to the details at least every now and then. So I think it's nice because before from Ranz we had a much more hydrogeosciences oriented introduction to fluid mechanics, let's say. I'm going to do transports. And my background is physics, right? So I'm going to be a bit more on the physicist side, let's say. But I'll try to connect to the previous talk as I go along. So I'll start with advection-diffusion, where we kind of forget about porous media and we just think of control volumes. Then I'll do some solutions, like I said, for simple ideal cases. I'll try to motivate why those are important for more complicated cases. Then I'll use that also to motivate the concept of mechanical dispersion, which ties into the REV discussion we had at the end of the previous lecture. And then, mechanical dispersion deals with large-scale spreading, large-scale macro dispersion, or dispersion at large scales. But when we're interested in mixing and chemical reactions and small-scale gradients that set reactions, there are other scales that become important for the problem. So I'll try to motivate that a little bit by talking about something called the Ranz transform and the idea of stretching, compression, and diffusion on little lamellar structures. I'll go very quickly on that though. Later in the week, people will fill in a lot of the holes that I will leave along the way. All right, so let's get started. I'm going to start with mass conservation, pretty much like the previous lecture, but it's easier for transport, at least in my opinion. So we have a little control volume that we imagine in our domain. It doesn't have to be a cube, but I don't draw very well, so mine is a cube, okay? But you can put whatever you want. Now, the way this works is exactly the same as we saw in the previous lecture. The idea is that the change in total mass inside this volume, which I'm going to call omega, let's say, is just the change comes from current going out, right? That's all I'm saying. So the J is the current going out. It's mass per area per time, just like we saw in the previous lecture. And here, if you have a little cube, you can just go on the faces. If you have a fancy volume, you can write the fancy integral. But this is just summing the current over the area. And the little ball, if you haven't seen it before, means the area is closed. It encloses the volume. That's all it is. Nothing too fancy going on. Okay. So now the thing is, for the problems that we usually treat, the current here, the mass per time per area, is an advective current plus a diffusive current, right? So the advective current represents stuff that is dissolved in your flow. So for example, a dye or a contaminant or whatever you have it. And it follows the streamlines in our approximation, let's say. So that goes into advective current. Then the diffusive current has to do with what we call Fick's law, and it has to do with small-scale microscopic motions, right? But I won't touch on that too much because at least Marco Dents later in the summer school will get into a lot of detail on that, right? So for now, for today, we're just going to assume that this is the case, and for the advective current, we are going to say, just like in the previous lecture, that it is proportional to V, that's the flow velocity, at the point we're looking at, and proportional to the thing being transported. So we're thinking of conservation of mass, in this case of a solute. So we have to put mass here, and it's being advected, so we have to put the velocity here. It should be proportional to both of these. The rest you can check by looking at units. If you look at the units of this, you do get mass per time per area, so we're good. That's it. In the previous talk, we had, you can have rho here, right? Like this is basically a density. So in the end, it's just having it proportional to what you need and then making sure your units are right. That's it. Now for diffusion, like I said, we're not going to get into the why today. Someone else will get into the why later in the week. We're just going to assume what's called Fick's law. We assume that the diffusive current is proportional to concentration gradients. That's the same C as the other one, even if it doesn't look like it. It's proportional to concentration gradients with a minus sign because, you know, stuff likes to go from where there's a lot of stuff to where there's less stuff. So that's what the minus sign does. And then there's a coefficient in front, which you may think of this as the definition of this coefficient. This coefficient is called the diffusion coefficient. And it has units of length squared per time, so area per time. Okay? We will have a more, let's say, operational view of what it does as we solve our problems. Right? So, yeah, that's basically all the ingredients we need. And now we want to write a nice equation using these ingredients. That's it, right? So what we're going to do is we're going to substitute the current on the right-hand side. Okay, so that's really all we're doing here. And then on the left-hand side, we're going to say, well, the mass is the integral of a density over a volume. Thing is, density of a dissolved substance, we usually call it concentration, right? So this is just the integral over the volume of concentration. I didn't write it here. You can write over the border of the volume if you like. But we know what we mean. Okay, so now the thing is like, this is an integral equation, it's a mess, there's like areas here, volumes there. We'd like to get everything together and get something that is true at every point. And the reason we think that we're able to do that is that I wrote this for a volume, but as I said, like, we don't care what volume this is. This is always true. It's just conservation of mass, right? So what we can do is just pull everything inside the volume and then express this guy through the divergence theorem, okay? So now, the first thing that you have to notice is that this time derivative can go right through the integral, okay? And that's because we're choosing a control volume that is fixed in our lab frame, or in the frame that we chose. When you're deriving Navier-Stokes or something like that, for those of you who have seen it, it's more involved, right? Because your control volume follows your Lagrangian little fluid elements. But here it doesn't, so it's easy. We just pass the derivative right through, right? I'm going to open some parentheses here. I'm going to pull this guy on the other side, right? So the thing is, we're going to use what is called the divergence theorem, right? So the divergence theorem just says that the integral over a volume, right, of the divergence of some vector function, so some vector field f, is just equal to basically the amount of that f, that is flowing out of your domain, right? If you're not familiar or not too terribly familiar with the divergence theorem, there is a way to convince yourself of this that is quite simple, right? Like you just take a little cube aligned with the Cartesian axis. You write down the definition of your gradient, which is just, you know, like partial derivative with x of the x component plus y of the y component plus z of the z component, right? That's del dot f, divergence of f. So if you do that in your Cartesian little frame, you will find that just using the standard fundamental theorem of calculus, these two things are equal. Right? You can convince yourself just by looking at the components. And then if your drawing skills are better and you do have a complicated control volume, you can build it out of little cubes. And the little trick is that the flux that's coming out of one cube, if it has a cube right next to it, is the same as the flux that's going into the other cube. So they cancel because they have opposite signs. Right? So then what you're left with is just the flux of your vector field over the boundary, which is exactly what we have in the divergence theorem. Okay? So, yeah, so now we can replace the area integral with the del dot and the dv, right? So I'm going to pull it in with the del dot, right, and the dv. I like dels because they behave like regular vectors. So del dot del is just the Laplacian. It's just the partial derivatives summed, right? So I'll write it here if you're not terribly familiar with it. For any function f, we just mean the sum of the x partial derivative plus the y partial derivative plus the z partial derivative twice. Okay? Yeah.
You're writing there v for velocity and v for volume. Can you maybe...
Oh, yeah. Thank you. It's nicer when you have it typed up, right? And I'll put some vectors as well. So I'll go retroactively fix, thank you, all the v's by u's. Please tell me if I forget. And I put some vectors there because dA is also a vector, right? In case we didn't talk about that, but dA is just a little area element, okay? And it's oriented according to the normal going out of the volume. Okay? Did I miss any little arrows? I don't usually put little arrows on the del, but you could. It's like a vector of the partial derivatives, right? Okay, thank you. So now we're in good shape, right? Because this thing doesn't depend on the volume, and the whole integral has to always be 0, right? So what that means is that we can just say that the thing inside has to be 0. Otherwise you couldn't make it 0 for an arbitrary volume. And that's it. That's the idea. You can put the terms on the side that you prefer. Often people write it like this. That's the idea. Okay, so one more little comment. Sometimes you'll see this thing with the u outside, right? That's just incompressibility. So the del dot, again, if you're not familiar with it too much, you can write out the expansion like this and check that it is true. The del dots obey the Leibniz product rule. They're like regular derivatives. The derivative of the product is the same of the derivatives crossed, right? So this thing is just u dot del c plus c del dot u, right? How do you know where to put the little dots? Well, this thing is a scalar, so this thing has to be a scalar as well. Make sure you have the dots in the right place. That's the easiest way, right? So for incompressible flow, as you're probably well aware, this thing is 0. Del dot u is 0, right? So this means that for incompressible flow, which we usually have or approximate as having, we can pull the u out, is what we like to think of it as. So if you've seen it that way, that's what it is. Do I have anything else here I want to say? No, I just want to say, so what did we assume when deriving the advection-diffusion equation? Not too much, right? But we did assume a few things that may not be obvious. So we assumed mass is conserved in our little volume. Seems reasonable, right? We assumed Fick's law. We assumed that the diffusive current is proportional to concentration gradients. As I said, I'm not going to get into why too much. You can see it as a consequence of microscopic motions as your little dye particles, for example, are hitting your giant water molecules at that scale. But Mark will talk more about that. We did also assume, I touched on that the transported little entities, let's say your molecules or your particulates that you're applying mass conservation to, we have assumed that they follow streamlines, right? That's not always true. If they're very massive or very big, they can have their own inertia, so they could run away from streamlines. But usually at the concentrations we're talking about and for the dissolved things that we are interested in, it's okay to make that approximation. Right? It's related to the Stokes number. And we did assume one more thing that is maybe more subtle. We assume that these little particles or molecules or whatever you have dissolved don't talk to each other. They don't interact, right? And that's usually fine at the concentrations that we're talking about, okay? If they can collide or something like that, then you could have interactions and the currents would no longer be linear, so the equation would no longer be linear. But that's a little bit more, less obvious that we assume that, perhaps. Now, just to finish this section, for mass conservation, we assume that in our little volume, like I said, mass doesn't change on its own. That's reasonable, but we could have situations where we want to model separately, for example, injection of some quantity or chemical reactions or extraction of some quantity. That's easy to do, right? You can just, conceptually, I mean. You can just come here and add a source or sink term to the ADE, and then you go check your units. So that's concentration per unit time, change in concentration per unit time. So just to give some examples to make it a little bit more concrete, let's say that you had, for example, radioactive decay, right? For radioactive decay, or any first order decay, your sink term, because it's negative, would be proportional to concentration. And in front you just have a rate constant, right? Units of 1 over time. Again, what you do is make it proportional to what you want it physically to be proportional, and then you figure out what the right units for the thing in front is, and you interpret that. Right? I think that's the practical way of thinking about these things. So just a couple more examples. Let's say that you were injecting fluid at a constant flow rate in here, or, well, let's do extraction, right? Like, let's say you are extracting at a constant flow rate. So if you're extracting locally at a constant flow rate, you're going to get concentration proportionally to how much is there, right? So you need a C in there. Now let's say you're doing it at a point, at the origin, for example. We usually represent that with a delta function. So that's a thing that's localized, right? And then we need a constant in front, right? Let's make sure. Oh, you will find that the constant in front is just the flow rate at which you are pumping. Okay? And you get that again by looking at proportionality. And there's a minus sign because we are extracting. So that's just an example, right? Okay, so the final thing that is left to do is to quickly discuss non-dimensionalization. Okay? So here we have our ADE. I'm going to maybe write it again here. We're going to forget about sources and sinks for the rest of the lecture to keep it simple, so no reactions for us today. Okay, that's our ADE. And now we'd like to know, often we want to know which of these terms is more important, right? And that's kind of obscured by the fact that we have, physical quantities with different physical units. So we find some length and time scales of interest, we normalize, and then we will have a better idea of what is big and what is small, right? So first what you do is you choose a length scale of interest, okay? It's really any length scale you want, but typically you want to choose one where the physics of the problem are important. So it might be the size of your domain, or it might be the size of a pore throat if you're working at in a porous medium, right? And then we define the diffusion time as L squared over D, and that's just a characteristic time that it takes for solute to explore a little region of linear size L, or of area L squared, by diffusion. Okay? And then we just consistently non-dimensionalize everything, right? We non-dimensionalize positions by, let's put some vectors, by the length scale that we chose. We non-dimensionalize times, no vector there, times by the diffusion time in this case. And we can also normalize, we can define our non-dimensional concentrations as now functions, or a function of these non-dimensional variables, and non-dimensionalized by some characteristic concentration scale. Depending on your problem, you could choose different scales for these things. An option is to use, for example, the initial total mass divided by the volume that corresponds to your length scale. You could use other things. Yeah?
So you also assume that the dispersion tensor is...
Yeah, so right now what I'm doing is I'm working on a little volume where I don't worry about pore structures, which will generate this kind of mechanical dispersion. So I will show you, I will introduce that later in the talk though. So for now, we're just assuming basic Fick's law coming from, again, subscale molecular motions. But we don't have any complications in the medium. So typically then you'll have isotropic diffusion or dispersion, if you prefer to think of it that way. And then we just have a constant here, and it does the same in every direction. But yeah, I'll get to that in a little moment. Okay, as I was saying, you can choose a concentration scale that's of interest to you to normalize. That's an example. You could also use your initial concentration, for example. No? So if you do this, the ADE, by judiciously dividing and multiplying by appropriate things, looks like this. And there's some, stars everywhere, and there's no D. Okay. I forgot to introduce, of course, we need a scale for velocity as well, right? So you could use, for example, the mean velocity, u bar, right? And then you just divide your velocities by u bar. Okay? So in this form, in the ADE, what you get is you get no proportionality constants anywhere except on one of the terms. That's why we chose these length and time scales, right? And the proportionality constant that you put here is called the Peckley number, right? Which you might be familiar with. It's just LV bar over D, okay? And then to understand what the Peckley number means, you can also write it as the diffusion timescale divided by an advective timescale for the same length scale, and that advective timescale, is just L over U bar. Yeah, so it's the time it takes by advection to cross a length L. That's all it is. Okay, so when you write it like this, you see that what this is representing is a diffusive timescale divided by an advective timescale, or if you prefer, an advective rate versus a diffusive rate. So when advection is strong or fast compared to diffusion, this thing is going to be fast, it's going to be large, sorry. And when diffusion is fast or strong, if you prefer, this thing is going to be small. So for our equation, what that means is that this term here, which if you remember came from the advective current, is going to be large compared to the Laplacian term and vice versa. So what that means is that your transported solute will follow the streamlines more or will diffuse around them more. So you'll have typically more heterogeneous shapes when you have large Peckley, whereas diffusion is better at homogenizing over heterogeneity when the Peckley number is small. We'll see a little bit more of that later on. Okay, so that's the ADE. There's really not that much more about it in terms of the concepts, I would say. So like I said, I think it's important to get the mass back, which is what concentration is for, right? So it's just a density that integrates to the right thing and starts concentrated at the point. Okay, so very important, this equation and also the ADE in general is linear. What do I mean by linear? I mean that it depends, there's no c squares, right? There's no squares or squares of derivatives of the function we're solving for. So that makes it much easier to solve and amenable to a lot of techniques. And a lot of them are based on this thing that you've probably all heard about called the superposition principle. And what that means is that if something is a solution and another thing is a solution, the sum of them is also a solution. What that means physically is that if I put a mass here and let it diffuse and I put a mass there and let it diffuse, the solution is just the sum of these two solutions. They don't talk to each other, they don't interact, right? So it's common to look at the solution for a unit mass. And when I mean unit mass, I really mean unit mass. The mass is one with no units, okay? And the function, the solution that corresponds to that is like a concentration field with unit mass, and we typically call it the Green's function or the propagator, right? It's called the propagator because it represents how a point initial source propagates. It's called the Green's function because a guy called Green worked on this function. That's it. So the point is that we are going to look for g of xt, we usually call it g for Green's function, which is the solution of the same equation, but with g of x0 equals just delta of x, mass 1, okay? So What else do I need to tell? Okay, so within an infinite domain, so the boundary conditions, if you like, at infinity, are what we call natural boundary conditions. That means zero concentration derivative. If you're confused as to why we can't put something else, the reason we can't put something else is that that wouldn't give us finite mass. Right? When you go and try to integrate, if you have things at infinity, you cannot control them enough to keep the mass finite. If you're more mathematically inclined, the solution wouldn't be in L1. But really, I think the physical interpretation is the more interesting. No, there's no way to put infinite mass there, so we have to keep it in check. Okay. I think that's it for the preliminaries. Okay, so how do you go about solving this thing? You can do it in many ways. Arguably, some are simpler than what I'm going to do. But I'm going to do it with Fourier transforms. And the reason I'm going to do it with Fourier transforms is that they're super useful generally for linear equations, right? So what's a Fourier transform? A Fourier transform is, if you like, just an integral transform. So it's an integral that you take over your function with some weights, and I'll explain what it means in a second. So I'm going to denote it with a little hat. The variable x turns into a wave number. I'll tell you what it represents in a moment if you haven't seen it before. And I'm going to use one of the multitude of conventions that people use, but they're all equivalent, right? So it's just this, okay? I didn't write it down, but sometimes it's also useful to write it like this. So the Fourier transform is an operation, it's an integral that you apply to a function, and then it becomes a function of wave number instead of space, okay? We can also go back, okay? So to go back is easy. We get the function back if we apply the inverse Fourier transform, which we apply to a Fourier transform thing to go back to being a function of x, okay? Again, I use one convention, there's more than one. This is, I would say, the one that physicists tend to use. But again, they're all equivalent. Okay, so what's the wave number? The wave number is, I think the easiest way to think about it is, if you have a sound, a complex sound, you can always represent it as a sum over harmonics with their own phases, right? So the wave numbers are the things that characterize harmonics. They're the wavelength of the basic sine functions that you use to build your function, right? And this thing is just pulling out the amount of your function that is in that wavelength, okay? If you're not familiar with this and that confuses you, you can also think of this as a convenient machine for turning derivatives in x into products in k, okay? That's what it does. So if you have a practical mindset, you might not care what it means. You can just go and apply this and you'll find out, oh great, it turns derivatives into products. Why is that good? Because this thing is a partial differential equation, right? They're hard to solve. If you get rid of this derivative, you have an ODE, an ordinary differential equation. That's way easier to solve. And this one in particular is super easy, right? So that's what we do, okay? I'm going to erase some boards, maybe over here. I don't think you need my name anymore. Or fancy little volume. Okay. I'll give a lot of detail on this one, then I'll speed up for the other cases. All right, so if you do that Fourier transform thing to the equation that's all the way over there, maybe I'll write it again here. All right. E2C, that's a 2. Just believe me for now, and even better, if you don't believe me, try it if you haven't seen it before, right? You do it by integrating by parts, okay? You take that integral, you integrate by parts, super easy, there's an exponential there, it's very easy to do. And you'll see that each time you want to pull out a derivative, you integrate by parts once, and you get some coefficients in front, maybe they have an I in them. When you get to the second derivative, there's no I, you get an I squared. That's actually, there's a bunch of plus and minus signs, be careful with them. In this case, you end up with a minus. If I did it right, I'm pretty sure I did. Okay, but like I said, I mean, this is an ODE, that's great. I mean, that's the easiest ODE you can possibly have. Derivative in time is proportional to the function with the thing that's constant in front. That's an exponential, right? You pull it over here, separation of variables, you get a log. you know. So the solution is just e to the minus k squared dt. That's super easy. Very neat in Fourier space. Looks, I mean, as simple as it gets, right? Remember what this thing is. It's the Green's function. It's the thing that propagates a point mass. But we're still in Fourier space. We're still in wave number space. So at this point, we want to go back, right? So you can use this other integral. It's very symmetric. It just has a plus sign there, and the 2 pi is a convention, really. You plug in that solution, that Green's function, and I'm actually just going to tell you the answer. Okay? You can do it by hand, absolutely. I'll even tell you the tricks. That's a Gaussian, right? Great. Okay, so the trick, by the way, is if you've done this a few times before, when you're trying to do the integral, you'll see an ikx and the k square, and your brain should be going complete the square, right? So if you haven't done it before, your brain wouldn't go complete the square, because it's kind of a crazy thing to do. But it's always the same tricks for these things. So it's nice to know them. And in this case, there are a couple of variable transforms that are easy to find that you can use. So I didn't mention it before, I should have. I'm following some notes that I put together for the class, and I'll give them to you, right? And so there's a little bit more detail in those notes, okay? And if you want to know how these little integrals, if you're that kind of person that wants to know how the little integrals are done, there's some instructions here. If not, you can throw them in your favorite symbolic calculation software, and it will also solve them for you. But it's nice to know a couple of tricks, have a couple of tricks in your bag, because they apply to a lot of things, as we will see in a moment. All right, let's go back to the physics, right? So this is the solution for just diffusion, right, with a point mass. Let's at least put advection back, right? Like, you know, it's the minimum we can do, no? So let's do advection now. But within 1D, so let's just do also a constant flow to the right. You can't really do much more than keep it incompressible, right, in 1D. So we did what we could, is what we say. No? So here, if you remember, the AD looks like that. But we don't care. That's the nice thing, right? Like, it's constant advection. Believe me, this thing is Galilean invariant, right? So it doesn't care what frame you're in. So you can just go to a frame that's moving with the flow velocity, and the solution should still look like that, because the physics don't change, right? So that's easy, right? What that means is that we just go to a new coordinate system where x becomes x minus vt. Is it plus? Is it minus? It's easy. When you are at the position vt, which is where the front would be vt time later, in this frame you should be at 0, and that checks out, so it should be minus. Okay? If you're ever in doubt, that's a good way to check. So, I mean, with very little work, we just put advection in. Granted, it's constant advection, but we did what we could. It wouldn't be incompressible otherwise. That's a good excuse. dt square root 4 pi dt. Okay. Great. So we solved the diffusion problem. We got the advection diffusion problem for free. So that's how a point source propagates, right? Let's just make sure we know what it's saying. I'll erase this one. Oh. This doesn't erase super well. I hope you guys can still see. All right, so I just want to do the mean and the variance of this thing. I think it's important. So what this is doing is we start with the delta function, which I can't draw, right? But it's an infinitely tall peak at just one point. And then it moves and it widens, right? So how does it move? Well, we can look at the mean position, right? It's a good way to have an idea of how it moves. So the mean position, which I'm going to call mu, but you can call it whatever you want, is just this. It's your concentration divided by your mass. The mass stays constant in this case, right? There's no reaction. But this is just the integral of the Green's function. Oh, what am I doing? x g of xt. And that's actually really easy to do. You can do the coordinate transform back, go here, and then you just use parity. Right? You're going to get a function that's odd. That part goes to 0. And then you get your vt from your coordinate transform. And then you get the integral of the Green's function. The integral of the Green's function is the mass. The mass is 1 for the Green's function. So that's it. You don't have to do it. You know it's 1.
You need another x, Tomas?
Yes, I absolutely need another x. Thank you. Otherwise, that wouldn't be true at all. Thanks, Kevin. Right? We're trying to do the mean of x. Right? By definition, we have to weigh x, the thing we want the mean of, the position, with the probability of being somewhere, the concentration field. Thanks, Kevin. Yeah, so that's the mean position, and that aligns with our intuition, right? Like this center point should be moving at the mean velocity. But the mean velocity is just the velocity because it doesn't change in this case. So we just get Vt. Okay. Then we can do the variance too, right? So the variance is, a measure of the square of this width, right? That would be sigma. We do sigma squared first, and that's just the integral of x squared, which gives you a measure of opening, let's say, width. We can just put g right away. Whoop. And then we have to subtract the mean squared so that we center around the place we're interested in, right? Because most of you have seen this before. And again, this you can do with more or less the same tricks that you already used to do the integrals here. It's just a change of variables, really. It's very easy to calculate. And you just get 2 dt, right? 2 dt. So that means that the width of this thing goes like square root 2 dt. We're all used to this and stuff, but that's super weird. Right? Like it doesn't grow linearly in time. It grows with square root of t. That has to do with the way that these random motions at smaller scales work. But again, I leave that for another lecture. I won't get into it. But don't forget that it's funny. The width grows a square root of t. It doesn't grow like t. You need a funny process to do that. I think that's cool. Okay, I think that's about... okay. And this is nice, right? Because, we just introduced this d thing as a coefficient in front of the gradient. It's kind of hard to know what that means, right? So a more operational way of looking at it would be just to look at this and say, d is just the rate of change of the variance. It's the way our plume is widening. That's what it is, right? Bummer, there is a bugger of a factor of 2. That's just convention, right? If you put a factor of 2 if you put the d in front of your Fick's law current, then here the rate of change is 2d. It's just convention. But it is what it is. It's a number, or a physical quantity, that is telling you the rate at which something that diffuses is growing at. Okay? Okay, so now, that was the longer one because I wanted to give more details, but I wanted to convince you, I'd like to convince you that the Green's function is not as useless as it sounds. It's just a point source. When do you have point sources? Remember, the equation is linear. So you can use the Green's function as a building block. Because if you propagate multiple things, the solution is just the sum of the multiple things that you're propagating, right? So the Green's function is more useful than it looks. And to illustrate that, but still stay simple, let's do a continuous injection, okay? Quickly. So for a continuous injection, there's multiple things we might mean by a continuous injection. In this case, we take a semi-infinite 1D domain, keep simple. This is the origin. And at the origin, we fix the concentration to be C0. Okay? So that means that C of x equals 0 t is C0. Okay? Now the thing is, what is this C0 doing? It's just putting mass into your domain according to the current, the advective current plus the diffusive current. Right? We learned in the beginning that looks like this. Oh. In 1D, it looks like this at x equals 0. Okay? Yeah, you have to integrate currents over areas, right? But we're in 1D. So integrating over areas is just evaluating at a point. It's just the units. Okay, so we're putting mass in because, you know, advection is carrying the concentration that we're putting there. But we have a gradient as well, so there's a gradient term. So this thing here is a function of time, right? And it represents mass per unit time being put into the domain. Okay? So now the trick is to use the Green's functions to find the solution. And it works out quite neatly. Look, we don't know what this is, right? In this particular case, we are imposing concentration. We're not imposing diffusive flux, because that's what we chose to do, right? So we don't know a priori what this derivative looks like in time. But there is a trick to find it. I mean, I'm sure you can find other ways to solve this, but I like this one. Okay, so the way we do it is to recognize that, okay, so at each time dt, the amount of mass that you're putting in is f of t dt. And you're putting that mass where? At the origin. Okay, so that's like a little dm. Okay? But if we multiply our Green's function by little dm's and then sum them all over, it's still the solution because of linearity. So we integrate and we propagate. Okay? But now we have to be careful about our times, right? And let's, you know, now this looks weird, right? Let's put the dt in the right place. So, sorry. Let's call it dt of t. So our integral looks right. And then we propagate this. But this is, so we are at time t. This is c of xt. We are at time t. But we have injected mass all the way from time 0 to time t. So we have to integrate over times earlier than t. But the mass then starts at x equals 0, propagates to x with the Green's function. But we only have time t minus t prime left to get there, right? So that's the solution. That's it. We don't need to compute to do more math, right? That's it. Actually, I'm lying, right? Because we still have to solve this. So we need another transform. So if you've seen this kind of thing before, you look at this, you go convolution, right? This kind of integral with the t prime and the t minus t prime is called the convolution. What does it represent? Well, depends on the context, but in this kind of situation is what I just told you. You put stuff there at a certain time, and then you propagate it until a later time. So you get this natural, right? So for this, sorry, there's another integral transform called the Laplace transform. It's really similar to the Fourier transform. We do it with the tilde. Or I do it with the tilde. It's Laplace of f. It's the thing that takes f's that depend on time to depend on lambda. Lambda is like a decay constant. And it looks very similar to the Fourier transform. But instead of wavy frequencies with the I, we have decay modes. Won't get too much into I, but it's the pesky little starting at 0 that makes you need to use this one instead. Okay? It's very similar to the other one, but the other one we were in an infinite domain, right? Now times start at 0, right? They start at a specific time when we turn this on. And that's why this thing behaves differently. You might notice that I didn't write the inverse transform. The little 0 looks like nothing, makes the inverse of this a mess. Okay, like you have to go in complex space, you have to integrate over a contour. I won't get into that. Okay, so typically what you do, don't worry, I heard some side there. So what you typically do is these things are tabulated, and for usual functions, you know what the solutions are. You just look them up, or you ask your favorite symbolic calculation software. Right? You can do them by hand if you really want to, but you know most people don't. Let's put it that way. Okay. So yeah, but if you allow yourself the luxury of Laplace transforms, they're kind of like Fouriers. They turn derivatives into products, and more importantly for this case, Fourier does that too. They turn convolutions into products. How cool is that? That's super easy to prove, by the way. You can do that one. So now we leave the x alone. We do the time derivative, the Laplace transform. And you just get that, right? So now comes the trick, right? Like this thing is valid everywhere, at all x for all times, right? So if we set c to 0, where we know we're setting this, right? Then we can find the flux from this. So basically the reason that you can do that is this is telling you if you want to keep your concentration constant, then you can't do just whatever you want with your gradient, because that impacts your diffusive current and your solution will be all wrong. So the information is there, right? So you set this to 0, you put C0 here, right? And then you take the Laplace transform. The Laplace transform of a constant is just that constant over lambda, right? So when you work that out, what you get is that in Laplace space, sorry, that's probably not a good place to write this. In Laplace space, the flux now has a well-defined form from what I was telling you. It's just F tilde of lambda equals C0 over lambda, and then your Green's function at 0 as well, Laplace. Okay, that's an F. And then you just go back and substitute, right? So the solution just becomes, did I write it here? It doesn't matter. This, and then you just plug it back, right? So it's C0, and then you get G tilde x lambda over lambda G tilde of 0 lambda. Yeah, we just substitute. And now, yeah, you go and look at your tables, use your favorite software, or if you really want to, do the integrals. But I mean, they're not as easy as the ones before, okay? So you substitute, you invert, the details are, or some of the details are in the notes. I'll just write the solution, okay? When we go back all the way to real space, I mean, this is a bit a mess with the, I hope you can see. What we get is, so this is the full solution. You could do it also for a constant flux, right? It's similar, it's actually easier. So if you like this kind of thing, you can try to use the same idea to do it with a constant flux instead of a constant concentration. You get a similar solution. Okay, so maybe some of you know about the continuous injection problem. Probably many of you do, right? And you're not used to seeing these two complementary error functions, probably. Okay? By the way, the complementary error function is just 1 minus the error function, and the error function is the integral of the Gaussian. So the error function looks like that. That's x. That's f of x. And 1 minus that is just the other one, right? So that's rc. So this is telling you is, you know, here you have concentration C0 because you said you had concentration C0, and this stuff is moving forward at a certain velocity because you have advection, and the front here is widening because you have diffusion, right? But there's two F's, right? And that's because, you know, we don't fix the flux like we just said. No? So to keep the C0 constant, you need to do some juggling, okay? But I hear you probably saying, I mean, usually, you know, I fit my experiments, or people use just the ERC. What's with this? That's because at high Peclet number, this term is small. Okay? So you might be scared by the exponential with the plus sign. That's not a typo. It does have a plus sign. But this thing decays even faster. It's a little bit hard to see, but it does. It's also here. So the thing is, at large Peclet number, when advection is strong compared to diffusion, the solution looks like this. Okay? It's just the first F. And that's the one that people usually use. Okay? It's the one that looks like that. It's just the front widening and going into the domain. That's cool. But actually, because of the way the approximation works, this actually doesn't work at x equals 0 and time equals 0 ever. Which is kind of cool, right? Like, that's the one thing that we said we wanted. We said we wanted C0 there. That doesn't do it, right? But it's okay, because at large Peclet number, very, very quickly, you go up to C0. That's all. Those are all things that you can do by checking how this term behaves at high Peclet. I have some notes here if you're interested. But that's the basic idea. Just know that it's kind of a funky approximation. It doesn't really work at 0 at early times. But it goes there very, very quickly, and it's very, very useful. That's clunky, right? Like, this is way easier to fit, to work with, to understand. Right? You'll get a similar story, like I was saying, if you do the same thing, but you apply constant flux here instead of constant concentration. You can use the same ideas to derive that one. All right, cool. I want to do one more. Okay, this is the last one. Last one is shear. 2D, how complicated is that? 2D. We've only done 1D so far. Shear. It's like, why are these things important? Are they so simplified? Yeah, but they're useful. You saw the Green's function, you can use it to calculate more complicated cases. The constant injection, I mean, people use it all the time. If you're doing microfluidics or column injection and whatnot, often you just care about the widening of this front and you can use this kind of solution, right? So often these, with caveats, they apply to more complicated systems. So I think it's useful to know where they come from, at least do it once, you know. Now we're going to do shear flow, okay? So we're in 2D now, because again in 1D you can't really do a fun velocity field while keeping it incompressible. So we're just going to do x, y. And our shear flow, we often write it like this, right? It's just a flow that's 0 at the origin and then increases linearly, but it goes just along the x direction and it increases just along the y direction, right? So we said to use u instead of v, and I already used v again. Sorry. So u of xy, no dependence on time, right? Is just there's actually no dependence on x, and we just do alpha, y, and then the x direction, right? This alpha is just, you know, it's just the slope here, and it's called the shear rate. It's called the rate because it actually has units of 1 over time, because it's spatial gradient of velocity. So 1 over length, length per time. So this guy is 1 over time. So that's what the shear rate is. It's the slope here. That's it. Okay. And this thing shears because, you know, it shears. That's it. I don't know how else to say. All right, so let's solve this one. It's Fourier again, okay? So Fourier in 2D is like Fourier in 1D done twice, okay? If you like that sort of thing, just quickly, you know, we now have an x vector, and what you get in the exponentials are just vectors dotted into other vectors, right? When you're taking your Fourier transform, f hat of k. K is now a vector too, because we have wavelengths corresponding to the two spatial directions. But this little thing, I mean, like that's just by parts in the backward one. All right. So when we go and plug this in, what we get is for the, oh, I didn't write the ADE, did I? Sorry. So the ADE for this problem is the same as before. We just plug in our new flow, our friend the shear flow, the XF. And now we got to keep the gradient squared here, the Laplacian, because we have d2x plus d2y, right? Because we're in 2D, complicated. Okay, so now we take our friend the Fourier transform in 2D, C hat, using those little rules. It's just integration by parts to prove it. Hop, hop, hop. K squared. See, K squared is just the magnitude squared of the k vector. It's kx squared plus ky squared. Damn, didn't work. I forgot I had it. Didn't work. Last time we got an ODE. But now, like the equation is still linear in C. But there's a y here. Sometimes we call these things quasi-linear. Doesn't matter what you call them, but the problem is, because of the y there, the Fourier transform didn't do the full trick, right? Like we still have a derivative. So why go through all the trouble of doing Fourier transforms? Well, this one, you can do another trick, okay? Which is called the method of characteristics. Right? I won't go into the details, but the idea is that there are some lines along the domain, and if you walk along those lines, the function changes in very nice ways along those lines, or doesn't change at all. right? So what I'm saying is, if you take the total time derivative over certain well-chosen lines, things simplify, right? That's the method of characteristics. So you can get rid of this thing because this is like an advective term, right? It's similar to this one, just in Fourier space. You can't get rid of that thing, right? So what you do, though, is you're turning this kind of advection-diffusion-like problem in Fourier space into a simple problem where only the diffusive component matters, right? So you can find what these characteristic lines are by finding lines where this term cancels for the total derivative. Or you can ask someone that has done it before and they will tell you, well, you can use these characteristic lines. Go along lines where the value of the second variable is related to time and the value of the first variable. It looks like voodoo, but the idea was this. Someone figured out that if you want to cancel that term, you can do it analytically. If you want this term not matter, what lines should I go on? They're these lines. That's it. When you don't see where they come from, it's, but. So what you do is you don't believe me, you take the total derivative, right? You take the total derivative, but now you evaluate it over these coordinates, right? And that's, I'm not going to really do it. It's the time derivative, but then it's, dc, dt. I'm actually going to write it like this because they, it's like they cancel. No? dt, wait, dc, dt, dt, dc. No. Sorry. Right. So that's the derivative with respect to the new variable. And the thing is, what comes from here, which comes from the equation, cancels with the stuff that comes from here, right? And you just get the diffusive part. So, we're almost done.
Thomas?
Yeah.
When you finish this line of thought, can you say something about parabolic profile, not necessarily linear profile, that you'd have more common?
For the shear flow. So,
I don't want to disrupt you.
no, it's okay. So the idea is that locally, this is always what you have, right? Except if you're at the minimum. So if you have a parabolic profile, looking like that.
Well, you can turn it on its head to make it in the direction of shear.
But you still have the problem. Okay, so if you're locally somewhere here, you are okay. Because close to the point, you can still use this solution. If the second term is really important, then you'd have to work for it. You can't just use this solution right away.
You don't have a voodoo solution?
I'm not aware of the top of my head of a voodoo solution for the y-squared case, but it might exist. So it's probably possible to solve, but I don't know the solution. Do you know the solution, Kevin?
It would just give you the second order ODE, or second order PDE analysis to that.
But then can you deal with it with characteristics as well? Probably not, because you have the second derivative is going to be difficult.
Okay, all right. Sorry.
I'll think about it though. But again, this is a bit more useful than it looks. We'll see that in a sec. Because locally, you can often use a linearization. But yeah, even the second order term is already difficult to deal with. That's true. That's the problem with theorists, right? So just to finish that idea, so the point is now, we have basically, again, an ODE, but I put a total time derivative, right? Because we now have this C variable. And that's you just keep the K squared term, which we now write like this. Okay? And this, you can solve. And the idea, I'm not going to do the details, but the idea is exactly the same as before, because now it's an ODE. It's still an exponential, but now this guy here depends on time. So you have to integrate inside the argument of the exponential. It's separation of variables. You put this guy here, you get d log c, then you integrate the other side, then you exponentiate. It's here if you're interested in the details. And then you do this step, then you go back here, you go back to kx, and you get your solution. Okay? And then you just play with it algebraically, let's say, until you get something that looks nice. And the usual way to write it, but it's really just algebra. Like the only voodoo is finding the characteristic. And it's nice because you can write it in this very neat form, right? Like K, P, A, O, do. And then K is, I'll tell you what it is. Let's just write it down first. Let's not get it wrong. Alpha T over 2, alpha T over 2, and then this is just 1, right? Okay, so look, like this is a Gaussian again, like before, but before we just had like K squared. And now we have to like rotate the K first. And we rotate it with this thing, which is the variance matrix. What is this? Like this is just, you put your little dot of mass, we're doing the Green's function again, right? So it's just a dot of mass at the center, and what does it do? Like it starts widening, but then it starts feeling the shear flow, right? So it will start widening like this, and you'll try to orient with the x-axis, but stretch. Right? That's important later. So now this is, it's like Gaussian here, but it doesn't widen the same way in both directions because there is a velocity gradient, right? And it turns out that the way that variance works is contained here. If you go back to real space, again, it's one of those substitution integrals. Ask your favorite software, or it's not, there's nothing fancy going on. And you just get x dot, the inverse of this matrix, x, that's the real space solution. Okay, we were still in Fourier. And then down here you have 2 pi square root of the determinant of this guy. Looks complicated. It's less complicated than it looks. Okay, so then I think the easiest way to make sense of this is, well, first to understand that it's just Gaussian stretching differently in different directions. And second, I mean, if you go and put alpha equals 0, you should get the no-flow result, right? And you do. So this just becomes the identity. So this is just 2 dt. So the identity doesn't do anything here, you just get k squared, same thing there. And then you get the dt's in front that come here. So what you get is a product of 2 Gaussians, one in the x direction, one in the y direction. And for each direction, they look exactly the same as they did when we did the Green's function in 1D. Right? Good. But then, there's this stretching effect, right? So here, one way to understand that is to look at the mean and the variance again, right? So if we look at, this thing does the variance, right? If we look at the mean, it's nice, we get 0. It's a vector now, right? Because it's xy, but it's just 0. And that's because we injected at the origin, right? So stuff is going here, stuff is going here. On average, it doesn't move. If you had put it here, it would move it with the average velocity from here. Right? And then for the variance, let's see, I have it, I don't want to write it down. Yeah. You can do it along different directions, but usually often we're interested in the variance along the mean flow direction, right? The longitudinal dispersion, right? So the variance, I just noticed I forgot a square in my notes, I'll fix it later, is 2 dt, which it was before. But now we have extra variance. And it grows like super fast, like t cubed. What is that? Well, there's nothing magical about this, right? Like it's just this, we're stretching because some stuff is moving faster than others. That's it. This stuff goes fast, this stuff goes slow, same here, it stretches faster, right? On the y direction, actually, you don't get this, right? Like you just get 2 dt because there's a 1 here. So because of the way the shear is oriented in this direction, you get mechanical dispersion, right? Like now we get to mechanical dispersion, right? And that's what mechanical dispersion is. That's it, right? It's just some parts of the plume go faster, some parts of the plume go slower, and that means your plume is going to deform in a different way. But now, look at this. We don't have to deform equally in all directions. In fact, we don't usually, because the fact that we have a mean velocity direction means that we break symmetry. Not all directions are created equal anymore, right? Or they're not equal anymore.
Can you say something about scales here? Because you started with the uniform cube.
Yeah.
And now you have shear flow, and I want know what is the scale that
Yeah,
you're
so
considering here.
that's what I'm going now. So I'll write down the advection dispersion equation, which we use at the REV scale typically with some caveats. So I write that down now. At this point, we're still in physicist land where we just have a simple problem and it doesn't care about scale, right? So for any flow where you have a shear flow, you would have this. What we didn't have though, and that's important, is we didn't have any grains here, right? So if you want this to relate to what's going on inside your porous medium, you're going to have to average over profiles like this in order to get how your dispersion behaves, right? So this is not something we did here. So here, there was no upscaling, right? Like we stayed at the same scale all along.
Yeah, so if you draw the cube that you wrote initially, you plot the shear flow over the cube and the cube domain, so I can understand.
No, so when we did the volume, okay, I see what you mean now. When we did the little volume didn't care where we were. So for this version of the ADE, for the diffusion equation, the little volume is everywhere and it's subscale as small as you want. So that means that this ADE that I wrote here holds at every single point. So at an arbitrary small volume, anywhere. The problem is that, and that's exactly how advection dispersion comes. Thanks for the... So now when we go to advection dispersion, we don't have usually access to all the details at the smaller scales. So we would like an equation like this that is only valid in certain bigger cubes, right? And that's how we get to advection dispersion. What I wanted to point out here is you do get mechanical dispersion for free even if you just have the ADE with no upscaling whatsoever. It's just that the scale at which certain descriptions are useful or not useful is different, right? So for a simple situation like this, we can just write the full diffusion equation that is valid at every point. We get the full solution, and then we realize, but it's still Gaussian. And now comes the next step. But usually we don't have that luxury, right? So that's exactly what I wanted to go now. So thanks for the segue. So now, that's the point I wanted to make, right? Like, so you realize that here you have a dispersion that works like this. It's different in different directions, and you realize, I can do this with exactly the same tools that I did before. But now, that's the question that was in the beginning too, I don't have a diffusion coefficient anymore. I have a diffusion tensor. What's the diffusion tensor? I don't know about you, but to me, it's just this, right? Like it's just the derivative of the variance along the different directions. But now we have directionality, right? Like we can no longer have a D that represents the growth in all directions. We now have to keep in mind which direction we are talking about when we talk about dispersion. If you prefer fixed law, you can still do fixed law, right? Like in this case, the dispersive current, if you like to write like this maybe, the dispersive current would look like this, right? And some people like to put the sum explicitly. Okay, so this is like for gradients in the J direction, how much dispersion do you get in the I direction? That's the I component, right? So you can think about it that way too. But really at this, to me, this is a bit magical, right? This is not, right? Like we saw it, you solve the thing and it does that, and it's Gaussian, right? So the point is, this thing solves an ADE where this guy is now I said I wouldn't use U. It's now a vector U bar. Maybe like that, I don't know. C, D, fancy D, C. Okay. So the thing is, okay, look at it. Like this thing here, even though it obeys an ADE at tiny scales, it also obeys a different ADE at bigger scales. Right? If you're just interested in what the plume is doing, if you just care about the concentration field, you solve this guy, you get the right concentration fields. Right? The solution to this, it proceeds the same way and you'll get the solution. So, if you didn't know what was going on at the smaller scales, you could go and measure that plume look, find out that it's Gaussian, find out how the dispersion grows, and write that equation. Okay? In that particular case, the average velocity that I put here is 0, but in general it wouldn't be. Right? In this particular case, the dispersion coefficient is like the derivative of this thing, like that, depends on time, right? Because shear makes it grow faster and faster because you're exploring more and more. More generally, what's going on is that these things, now comes the question of scale. Now these things represent averages over some subscale that you're no longer representing explicitly, right? And from a practical standpoint, you don't do this, right? Like you don't go and solve the small scale thing and then you get that. No. You go, measure something, you say, it looks kind of Gaussian, it spreads in a certain way. What equation does this solve? Solves that equation. And that's called the advection-diffusion equation usually. Confusingly, we also call it the AD. But really, I mean, it's the same equation, right? Like it's just that now the dispersion tensor is not necessarily isotropic. You can spread in different ways.
But right? It has mechanical component in it.
Exactly. So this will be composed of some small scale diffusion that is usually very small in the problems we're interested in, and some component that has to do with these kinds of stretching effects by the velocity, right? And that's what we call mechanical dispersion, right? So there are many ways to go about this. In fact, it doesn't always work because the fact that we have this is somehow related to the idea that we have an REV that we can associate with every point. Locally, we can average out things. So for example, here we could put the Darcy velocity, and here we could put, the variability in velocities that will give you dispersion, but Marco will talk more about that, okay? I won't get into details there. So there's lots of theories for how you get these guys, and this doesn't even always work. Sometimes Fick's law, which essentially is still here, doesn't hold anymore. And actually a symptom of this is what we were talking about before. It's the fact that when we measure these dispersion coefficients at larger and larger scales, we don't always get the same value. And they often scale like power laws. That's an indication that maybe there is a better description for some problems. But often in practical terms, I mean, these are the things that we can measure, and this will at least give you an idea of how much your plume is spreading and how much it is moving. So even if it doesn't work perfectly, often it's still a good model, right? So one model that people use, again, Marco will give you details on how to upscale. The one model people often use is this thing that is sometimes called the Baire dispersion tensor. And the idea of the Baire dispersion tensor is just to say, look, if we have a situation where locally at the small scale with isotropic, the pore structure is not complicated, doesn't have a preferential direction, but we do have a mean velocity, or we do have a local velocity, the only thing that should be able to make dispersion non-isotropic is the velocity that's breaking your spatial symmetry or spatial isotropy. Right? So you just build a generic object that is a 2D tensor, and that depends on the velocity field and on small scale diffusion if you want to put it in. Right? So I write it in the general form, then I'll explain what it means. Okay? Here you just put U bar. This looks complicated, but it isn't. I'll tell you now. Oh, I said I would use U. Okay. So, this looks complicated, but that's just because we are in an arbitrary frame. Okay. So now we go to a point. I mean, the velocity can change, so we can't do it everywhere. But if you go to a given point, we can align our coordinate system so that the velocity is along the x-axis. Right? And then you just have, did I do it? No. I did do it again. Thank you. So U bar in that coordinate system, right, aligned with the velocity, U bar x is U bar x, but it's just the velocity, right? It's actually U bar at that point. But U bar y and U bar z are just 0 because we just aligned our velocity, our frame with the velocity. So in this frame, this looks much nicer, right? Like we just get that the components look like this. we have a longitudinal diffusion coefficient, that's DL, sorry. So the board is getting. And then we have transverse dispersions along the other directions. I mean, you could make them different if you wanted. But often people use this kind of formulation, right? And then in this frame, DL is just molecular diffusion plus the mechanical dispersion term we were just talking about. And what this does is assume that the mechanical dispersion is proportional to U bar, not V bar. And the same thing for the transverse direction. And then the complicated deltas and minuses and whatnot are just to make sure that if you rotate to a different frame, this remains the same object, right? But if you go to the nice frame where things make physical sense and you align with the velocity, it's just this. And this is just that, right? Except now it doesn't depend on time because we're assuming it depends on some averages of properties over some REV locally. Again, I'm not going to do that today. Marco will get into that more in detail. Okay, so these things, these coefficients that show up are now called dispersivities. They have units of length, usually measured in meters or centimeters. Okay? And we assume that this component is proportional to velocity because velocity is what is doing the extra work to stretch. That's the idea. I haven't put any numbers, right? Like that's theoreticians are weird. I'll put a couple of numbers now. So just like I said, these things depend on scale, which is a symptom that there are other effects going on that I won't go into today. But if you go and measure this at face value, how do you measure this at face value? You throw some stuff in the ground, while later you come back, you check out where the mean position is, and you check out how dispersed it is. You assume, for example, that form, and then you see what number you need to put in to get the right dispersion. And yeah, of course it's not that simple, but that's the idea, right? So if you go in aquifers at scales of about 100 meters, I mean, these are going to be very rough estimates, right? You can find other numbers around. But let's say that longitudinal dispersivities are typically something like 10 to the minus 1 to 10 meter. Remember they're in units of meter. Transverse dispersivities are usually much smaller, like 3 orders of magnitude smaller, or 2 maybe. And in the classical picture, often we're more interested in the longitudinal dispersion because it's more critical, it's larger, right? So let's say you use a flow velocity, okay, U bar, just for estimation purposes. Let's say it's about 1 to 10 centimeters per day, right? Just some round numbers to get an idea. So if we do that with these, again, rough estimates, you will get longitudinal dispersion coefficients that are on the order of something like 10 to the minus 8 to 10 to the minus 5 meters squared per second. Right? Usually it's more like 10 to the minus 6 is the range you find. But in any case, even with these rough estimates, you already see that this is much larger than your typical diffusion coefficient. Because your typical diffusion coefficient, if you think about salt in water, for example, is something like 10 to the minus 9 meters squared per second. Right? So even on the low range of the estimates, and that's a pretty low range of the estimates, it's way bigger, right? Like a good factor of 10. Yeah?
I think we are running out of time.
Okay, I'll finish here with the... So, with these estimates, what you find is that the Peckley number, which is LV bar over D, if you remember, if you are, so in this case, longitudinal dispersion, if you neglect the diffusive part, you will find that the velocities cancel out. That's how this thing is designed, right? So you get length scale over dispersivity, right? So that's a nice feature of this dispersivity formulation. It's kind of directly telling you what your Peckley is at the scale of interest, right? You're comparing two length scales. And these numbers, if you again do these very rough estimates, they come out to about 10 to 10 cubed, which is a pretty good rough estimate. Typically you'll find something on a few tens to a couple hundreds is usually what you'll find. So the conclusion is that at these scales, about 100 meters, really macro dispersion, you're typically advection dominated. Advection plays a very important role. Okay? So I think honestly this is the part of the lecture that I really wanted to get through. I do have another section in there about mixing. Just a small introduction. I won't get into it now in the interest of time. But the idea is, just to leave it in the air, is to say that the picture that we are talking about here, if you have a complicated plume like that, the picture, the classical macro dispersion picture, is telling you about the width of the plume and where the average is. But it's not telling you about the complicated structure of the plume at smaller scales, which can be very important because that small structure is what controls local gradients. And local gradients control diffusive currents, and so they control mixing and chemical reactions, which occur at smaller scales. So the interesting thing is that you can adapt many of these ideas, essentially around the shear flow picture, although it's a little bit different, to locally think about the way these little stretched structures that form as you advect in the heterogeneous flow field will set the size of these structures and the gradients that you find. That's the idea behind this lamellar description of mixing. And well, I'll send you the notes with a quick introduction, or you can also sit down with me and we can discuss it together. So I'll stop here. Yeah.
I won't pester you too much, but
No, it's good.
when you do the alpha times u bar, you're making an assumption that the mechanical component of the dispersion is linear with velocity. It's not always the case.
That's correct. Yes, I didn't say that. So aside from the fact that here I said we wanted something that whose direction was defined just by the velocity, I'm also getting rid of higher order nonlinear terms. So that's absolutely correct. This is something that, I mean, so the thing is, this kind of picture is approximate in many ways, right? Because often we no longer have Gaussianity and whatnot. So going to higher order terms is not always
Contradiction
with what I get for shear. Oh yeah, but this guy doesn't depend on time either. This is time, but this comes, I think, more in this case because, so first, shear is not the same everywhere, right? And then also because here we are growing and growing and exploring and exploring, whereas here the idea is that we're taking averages locally over everything that you could ever explore. And that's why typically you can get away with no time dependence. That's not always true though, so yeah. But you're absolutely correct, of course.